Is Eric Bersin. I'm a PhD student at MIT in Dirk England's group, and I'm going to talk a little bit about frequency conversion, specifically in the context of quantum networking. So why do we need frequency conversion? So when we talk about quantum memories for quantum networks, most of the promising quantum memories that I think we'll hear about later at some point emit their photons that we would use for actual networking at visible wavelengths. And these are lossy in optical fiber, as you can see from this plot over here on the bottom right. This is wavelength, and then this is the attenuation as a function of length of the fiber. And so what we would really like is to have memories that instead of emitting photons that were in visible wavelengths, which are sort of south of here, we would rather have our photon emissions happening in one of these two bands, either the O band, which kind of runs from 1260 to 1360 nanometers over here, or the C band, which is sort of 1530 to 1565. So just to get a sense of how impactful this could actually be, if you were to have sort of one of these very popular quantum memories emitting at their native wavelength, this is a table that shows the loss per kilometer. And then if you were transmitting this memory at a 1 gigahertz rate over the Boston test bed, so going from Lincoln Laboratory to MIT, which is a 43-kilometer fiber link, these are kind of the rates that you would get at the end of that. So you can see that it's basically, impossible to have a functional quantum network using memories operating at their native wavelengths, and you really need to be converting to one of these lower loss bands. So how do you actually do that? So typically, this is done using some type of nonlinear material with either a Chi2 or Chi3 nonlinearity. So periodically poled lithium niobate, or piplin, is an example of a Chi2 material. Silicon nitride is very common for Chi3 type approaches. And sort of the basic idea, without getting too much in the details, is that you have your visible wavelength and you pump it with some other frequency. And the interference of these two, mediated by the material, spits out, basically converts this visible wavelength to some telecom wavelength, obeying the relationship here. I should say this is for a Chi2 type interaction. If you're doing something with Chi3, you basically just have two pump photons as opposed to one pump photon. So just a 2 in front of this pump. Now, the big problem with this as a practical matter is that this pump is typically something like hundreds of milliwatts, and that creates a lot of noise. So if you can kind of look at the frequency spectrum here, so imagine your visible photons over here and your telecom photons over here around the pump, but there's a bunch of noise generated by various processes in the crystal. And as a matter of practice, that restricts the parameter space. I'm going to flash a sort of confusing looking plot here, but basically what is going on here is on the x-axis is the distance between the telecom wavelength and the pump wavelength, or this is in wave numbers. On the y-axis is the converted wavelength that you end up in. And as sort of in this space, one can kind of draw lines through it based on various starting frequencies. So for example, if I had an NV center, this is sort of the range of places that I could convert that NV center's wavelength to. And we can see that there's no way for an NV center to be converted to one of these low loss telecom bands, the blue or the green, which is O band and C band respectively, without being in one of these regions of large noise. Another constraint on this is that the pump typically needs to be around 100 milliwatts, and that's just, as a matter of practice, not always available at whatever arbitrary wavelength you need to get some visible wavelength to the telecom frequency that's desired. And then this Chi2 versus Chi3 is also an open question, I would say. So there is some ongoing work going on in the CQN. I can talk to the work that's done in Dirk's group in collaboration with the Fayer group at Stanford, and also working with Lincoln Laboratory and some folks at Harvard. We are converting silicon vacancy emissions from 737 to 1350 nanometers, which is in that O band, using a 1623 nanometer pump. And here's sort of a diagram of our setup. And ultimately, we're filtering out that noise with a 50 gigahertz fiber filter, and just to kind of refer to that previous diagram, that obeys this sort of relationship where this telecom frequency is at a higher frequency than all of this gross noise over here. And so as a result of that, we're able to get relatively low noise counts, something like 100 counts per second on top of our detector dark count level. And we anticipate this should permit something like an SNR 50 using some sources that are available of silicon vacancy photons. This could be improved with narrow filtering. And another thing I'll just throw up on here without talking about too much is that another option rather than down converting to 1350 would be to up convert from 1350 to 737. So for example, instead of doing this option number 2, which would be both silicon vacancies emit at 737, we convert them to do some type of Bell state measurement. We could start with a entanglement source, like a spontaneous parametric down conversion source, or SPDC, and then up convert that, and they may result in lower noise and as a result higher SNR.